how did you actually carry out the experiment with the alpha G device?
The first thing we had to do was to change all of our thinking, because every trap that we'd built up to this point was a horizontal trap. And if you're trying to study gravity, obviously you want a vertical trap, something aligned with what you think is going to be the direction of gravity. Turns out to be the direction of gravity. And this sounds simple enough. You just take your trap. No, it's not simple at all. Among other things, the particles are still coming in from the CERN complex horizontally. So the first thing we had to learn to do is to make them go around a 90-degree bend. That was a really hard problem, which was actually solved very, very nicely by a graduate student. So now what's the next problem? The next problem is that even though they're very cold, they're not actually that cold. And they're moving pretty fast. So one way you could imagine that you would measure the effect of gravity is that you could just let them go upwards like in a water fountain. And eventually they'd reach some maximum height and they turn around, and the turnaround point is set by gravity. It's like throwing a baseball upwards. No matter how fast you throw it, eventually it's going to reach some place and then it's going to come back down. It turns out that our particles are, even though they're half a Kelvin, they're still moving so fast that they would go hundreds of meters high into the air. We use the fact that the antihydrogen atoms are repelled by strong magnetic fields. That is the whole basis of our trapping. So what we do is we have a lower coil down here and an upper coil up here. And we're very, very careful to make sure that they have exactly the same field. And initially, our atoms are trapped somewhere in between. They're trapped something like this, and they go up and down and up and down. And they'll do that forever, really. And then if we slowly lower the field, so we have these two strong magnets, and we slowly make them smaller and smaller, lower and lower fields, what will happen to the orbits is now they'll be able to get up the side of the bathtub, up the hill, further and further. So they started out doing something like this, and eventually their orbits will get extended and extended until they're just about making it out of that bathtub, but not quite. And then if we lower the field still further, then they'll be able to go out of the bathtub. They'll fall out. Now, if they escape up, and they'll hit something up there because they're no longer confined once they get out of our bathtub, and they'll annihilate. And that makes a signal that we can see. Likewise, if they were going down at the moment that they can escape, they'll escape, get out of our trap, they'll go in the trap, hit the wall, annihilate, and we can count that. We can see how many went up and how many went down. And that's going to be the basis of our experiment, except that I left out one part, gravity. So what does gravity do? Well, assuming, as it turns out, that gravity makes the antihydrogen fall downwards, what that means is we started out with these magnetic fields, which are strong. But gravity adds this downward force, which makes the field at the bottom just slightly weaker, ever so slightly weaker. And that means an antihydrogen atom, as we slowly lower these fields, it takes these bigger and bigger orbits, but is always going to go microscopically further downwards, further up the hill of the magnets on the bottom side than on the top. And that means that a preponderance, it's not going to be all of them because it's a statistical problem, but a preponderance of them are going to fall downwards. We can count that, and that's the essence of our experiment. We counted the ones that fell out of our trap on the bottom and compared them to the ones that fell out on the trap on the top. More of them fell out on the trap on the bottom, and that's how we know that gravity acts for them to go downwards.